Thank you for coming. Today we welcome Wannes Hubau. Wannes is a forest ecologist here at the museum, and together with his colleagues, he published an article last week in Nature. And for those of you who don't know about Nature, Nature is one of the most prestigious scientific journals. And their article reveals that the tropical forest, the capacity of tropical forests to remove carbon from the atmosphere is decreasing. And this, of course, has direct implications on climate change and climate change policies. And you might have heard of this study because despite the coronavirus frenzy, his work made the news. Wannes was all over. There's been over 100 news articles published around the world to report his study. And to know why this is so important, that's what Wannes is going to explain to us today.
Thank you very much, Jonas, and thank you very much to everybody who came to hear my talk despite the circumstances. So I will present, as Jonas said, our newest paper published in Nature as the cover story. It's called with the difficult title, Asynchronous Carbon Sink Saturation in African and Amazonian Tropical Forests. And it is my aim today to explain a little bit to you what we are actually showing with this. So as Jonas said, our article was published last week, Wednesday evening. And since then it has been picked up by more than 100 news outlets, including the Washington Post, Le Monde, Radio Okapi. Still going on. This morning I had an interview with VTM News. So we are very happy that our research interests so much press. So yes, I will start my talk with an elevator pitch, very briefly, which very briefly says what we show. Intact tropical forests are well known as a crucial global carbon sink. It is slowing climate change by removing carbon from the atmosphere and storing it in trees, which is a process known as carbon sequestration. And climate models typically predict that this tropical forest carbon sink will continue for decades. However, our analysis now shows that this will not be the case. And to show you, my presentation aims at showing you why this is, and a little bit explaining this elevator pitch. To do so, I start with an introduction on the global carbon balance. I think not everybody is as familiar with that as I am, so I'm briefly explaining how it works. So our planet has 4 major reservoirs of carbon. The most important one is the Earth crust, which contains most of the carbon, but which is quite stable there. Then we have the land, representing the forests, boreal forests, temperate forests, and of course tropical forests. Then the oceans, and then the atmosphere. And the numbers here are all expressed in gigatons. Gigatons or billion tons giga is a 1 with 9 zeros. So a lot of carbon, from which a very small amount is in the atmosphere. However, all these reservoirs are exchanging carbon, and there is a natural balance of fluxes between these reservoirs. So there is there are important carbon flux, natural carbon flux from forests, from the land, and from the ocean towards the atmosphere because of respiration of organisms. Respiration brings CO2 in the air. What we breathe is actually for a large amount CO2. But then an almost as big flux is gross primary productivity, we call it. It's actually trees are growing, and by growing they take that almost the same amount of carbon out of the atmosphere. So these fluxes are in a natural case in balance. And there are also a few smaller fluxes between the Earth crust and the oceans because of weathering and sedimentation. But, however, this natural balance has been disturbed since the Industrial Revolution, about 200 years ago, when we started large-scale burning of fossil fuels. This research is a big collaboration between the AfricaMuseum and, for example, Leeds University. And I always like to show this image of Leeds, which was a well-known industrial city. So Leeds has contributed a lot to this study, but also contributed in the past a lot to the emissions. But we are not only contributing to emissions, to CO2 because of fossil fuel emissions, but we are also changing the vegetation of our planet. And this is an example of forest fires and peat fires because of human destruction in Indonesia in 2015. You may have seen this in the news. We also see a big effect of climate change now on forests in the Amazon, and also the Australian bushfires are now a hot topic in the news. All this is actually an impact of climate change, the visible impacts of climate change. So we are bringing new sources of carbon into the atmosphere. But how large are these new sources of carbon? I'm always referring to 2015, around 2015, as a reference year, because our data is especially big in 2015. And in 2015, humankind emitted about 10 gigatons of carbon per year. 9 tons of these emissions were from fossil fuel emissions, and 1 ton was from land use change, such as the peat fires in Indonesia. So how does this relate to our little schema here? So the white arrows are these natural fluxes, but then now the big black arrow shows where we can situate fossil fuel emissions. There's 9 tons of fossil fuel emissions due to industry, for example, and then 1 ton from changes in the land, forest destruction. But fortunately, nature compensates for our excesses partly by providing sinks of carbon. So the same forests, they are being cut down, but because more CO2 is like food for the trees are growing faster, so they sequester also more carbon. Same thing happens in the oceans. Organisms in the oceans, they also sequester more carbon than usual. So I added 2 arrows which show this effect. So from this 9 + 1, from this 10 tons of carbon that is released to the atmosphere, 2.6 tons goes to the oceans and 3 tons goes to the land. But 4.4 tons stays in the atmosphere, and that is what is quite worrying. So I often show this graph because some of my colleagues tend to question the importance of CO2 in the air. There are other greenhouse gases, but this actually shows that CO2 in the air is responsible for 60% of global warming. So this 4 gigatons of carbon per year remains in the atmosphere as CO2. However, although annually this 4.4 gigatons remains in the atmosphere, we have to stress that land and the ocean carbon sinks absorb about 5.6 gigatons. So these sinks are really important. If they weren't there, or if they would not do that, there will be far more that will remain in the atmosphere every year. So these ecosystems, the oceans and the forests, provide an important ecosystem service to mankind. But the big question is, will this always be the case? And we focus, of course, our team of more than 100 co-authors. We are all tropical forest ecologists, and so we focus on the tropical component of the land sink, these 3 gigatons of carbon. What is the evolution of this, and what will the evolution be of this carbon sink? Will this always be 3 tons? How has this evolved in the past? So we are trying to entangle how stable this ecosystem function is. Tropical forests are important reservoirs. They represent 20% of the land carbon that is there. So tropical forests represent 20% of the land carbon reservoir, but they also represent 33% of the land carbon sink. So from this 3 tons, about 1 ton per year goes to intact tropical forests. So intact tropical forests are really, really important in the global carbon balance. The questions of our research now: what was the evolution of the tropical carbon sink over the last decades? But then also, what are the drivers of the sink? Can we understand how the sink works? And then something that we are more and more interested in is how does the future of the sink looks like? First, I'm going to explain a little bit about the methods before we plunge into the answers to the questions. I will plunge a bit into the methods. So what we do are direct measurements of carbon fluxes. We work in permanent forest inventory plots, and we have a lot of those plots. So each plot is about 1 hectare. I will show a few pictures after this. And all the plot data is curated in large databases. I always show this. These databases are, for example, Rainfor and Afritron. If you're interested in them, you can just look for them on the internet. But we have a large amount of plots that are curated there. From those plots, we have to carefully select the ones that we can use for our analysis, because we are interested in, first of all, intact forests. And I think my colleague Theodore Treffon made clear in his talk a few weeks ago that it is not easy to find intact forests these days. So we really try to select only those plots that are now still located in intact forests. We use only the plots where all the trees have been measured with a diameter and reference height more than 10 centimeters. So for the big fluxes and the big reservoir, we focus on the trees that are already a bit substantial. We only take the plots that have been measured at least twice, because we want to calculate growth and mortality within a plot. So we need two measurement points at least, or preferably even more. And we focus only on plots that are sufficiently large. 0.2 hectares is the limit, but usually our plots are about 1 hectare, 100 meter by 100 meter. And then we have a few environmental variables to define rainforest, to be able to set limits to the plot data: altitude, temperature thresholds, precipitation. So just to show you a few pictures of how these plots look like, they are usually square plots, 100 meter by 100 meter, divided in subplots. These are the picture in the middle shows how we demarcate in the field, how we demarcate each subplot by using string, by using rope. So that we are sure that we only measure the trees that belong to this 1 hectare, and we do this over and over again. So at each time when we come back to a certain plot, we again put the ropes to visualize the subplots and to be sure that we don't measure any tree that is outside the plot. Some of our plots, unfortunately, they are located in intact forest, but over time, some of our plots are more than 40 years old, have been measured since the 60s. And some of these plots have had some damage because of illegal logging, unfortunately. But our subplot system, we use our subplot system to be able to exclude subplots from the analysis. Subplots that have been disturbed too much, we can exclude them so that we can keep part of the plot for the analysis. The aim is to remeasure the trees. So it's easy to install a plot. You demarcate an area of 100 by 100 meter. Well, it's not easy, but it's one of the more easy parts. Each tree gets a number tag in the forest, an aluminium plate attached with an aluminium nail to the tree, and we put a mark of paint on the tree where we actually measure the trees. And this point of measurement is very, very important, because we want to follow up these trees for decades. Typically, we go back to a certain plot every 4 years. So we want to measure the tree on exactly the same place to be able to capture the growth of the tree. These are a few images to give you an idea of how a fieldwork looks like. We have now quite a lot of papers that have been published just on the methodology of doing this in a correct way, and doing this in a representative way and in a repeatable way. So what you see here seems to be easy, just measuring the diameter, but it really needs to be done in a very, very careful way. What represents always a big problem are these huge buttress trees, which we typically have in Africa. So we have protocols for that as well. And we aim to measure above the buttresses so that we don't measure the buttress creep. So all this is just to show you that our research, we aim to do our research in a robust way using well-published protocols. So these are a few other examples of how we indicate carefully the point of measurements, so that we can create time series. Then just a few images of how difficult our work is. Sometimes people think working in the rainforest, it's really nice. You're always outside, happy in the forest, but it's not always the case. Sometimes you go through very big challenges. For example, to reach our plots in Salonga National Park, we had to travel for a week in a dugout canoe. And we had to take all the food with us, all the fuel with us. So we needed to buy 9 barrels of fuel to reach Salonga National Park. And we needed to buy a lot of rice to be able to feed a field team of about 10 people to work on the plots for 2 months. So it's quite challenging to really do this in all these different forest plots. In the field, of course, you have once you arrive in the forest, you have again other trouble apart from transport. So there are a lot of animals that can disturb you, but also it's sometimes quite dangerous. So in the case of Salonga, we had to take a ranger with us because there were still quite a lot of elephant poachers around. So there are risks to the field work. Also, yeah, you have to adapt to local food. You have to find food that does not rot in the forest. So Congolese colleagues will recognize the makayabu, the salted fish on the left, or the mbinju, the caterpillars, which we find in the forest. All these things are things you can't eat in the forest when you camp for 2 months in a row. You have to use sometimes things that you find in the forest, but you also have to bring food that doesn't rot. So it's logistically quite challenging. Yeah, also the picture in the bottom shows that elephant poachers are around. So also once you are in the field, you don't take any rest. So it's 2 months of just working. And the trees are not always easy to measure. So the tree on the left shows how challenging it can be to measure a diameter on a large tree. You have to go above the buttresses, but also behind lianas. And all trees can have very big lianas wrapped around them. And we cannot cut lianas because lianas are part of the rainforest. So cutting them would introduce a disturbance. So we have to dig small holes in between the lianas and the tree to be able to measure the diameter of the tree and not the liana. The image on the right shows an elephant pathway. The tree we are measuring there is used regularly by elephants to scrub themselves. And in the case of Salonga National Park, our plots were crisscrossed by elephants. So it's an additional risk you always have to face. You don't want to meet an elephant in the field. So all these show how challenging it is. But I think we can say that our results are impressive. We now have the largest network of repeatedly measured plots in intact rainforest. My results are also about the Amazon, but I showed the map of Africa here to show you where the plots are located. And we cover the Central African rainforest kind of with, I have to say, quite some gaps still in the Congo Basin, but more on that later on. So our largest network of repeatedly measured plots in intact rainforest, we're talking about 244 plots in Africa, representing a bit more hectare because some plots are larger, 278 hectare. In Amazonia, we have 321 plots representing 343 hectares. Africa, 11 countries, Amazonia, 7 countries. Africa, 47 years of monitoring. The oldest plot was installed in the 1960s. More than 130,000 trees measured in Africa, and more than 390,000 measurements, because all trees were measured at least twice, sometimes even more. The data in Amazonia, we have a comparable amount of trees, but many more measurements. The plots in Amazonia have been measured more intensely. They have more resources and they have more projects. So that's why Amazonia is a bit better known, and this is our study for the first time now is able to show these long-term trends for Africa. So that is why our African database, although it's a bit smaller, it's now very interesting because it's the first time we present this. Most plot data is curated by on forestplots.net from Leeds University, but of course many researchers around the world have access to that database, contribute to that database, and during my 5 years here on a BELSPO project in the AfricaMuseum, I have worked a lot on data quality assessment within that database. Then a little bit on the methods. I'm going to try not to disturb you too much with calculations, but I'm afraid it's necessary for your understanding. How do we calculate carbon content? in a tree and in a plot, and then how do we calculate the change in carbon content over time. And just going to show you very roughly a few steps that we do to go from diameter measurements, but we also have height measurements of the trees, which I didn't show any pictures of, and wood density measurements. So these three things, diameter, wood density, and height, give an estimate of carbon via allometric relations, as the one I showed here. So these measurements enable us to estimate carbon content for a tree for each census. And then to estimate carbon gain from tree growth for each tree, for each interval between subsequent measurements, divided by the interval length. And then we express this carbon gain in tons of carbon per year. So we measure trees on average every 4 years. So we actually measure how much carbon comes into a tree, and we express that in tons of carbon per year. And then we sum these carbon gains of all these trees in a plot per interval again, and we divide it by plot area, and then we can express the gains of the trees of the carbon in tons of carbon per hectare per year. So it's quite a complex measurement, but this is calculating a flux of carbon from tree measurements. And then we also calculate carbon losses because we want to make the balance between carbon additions to the forest and carbon losses from the forest. And carbon losses are actually just the sum of carbon from all the stems that died, of all the trees that died during an interval, divided by the census interval length and plot area. This is quite complex and well explained in the paper. We have a very long method section, but this is just to show you that we have carbon additions and carbon losses. We calculate two fluxes. And then the balance, carbon gains minus carbon losses, the balance is the net carbon change, which is actually the sink or the source if it would be negative. So to visualize this, I give the example of just one plot in Liberia that has been measured for the first time in, I think, 1978. First measurement, then the second measurement was done, I think, in 1988. Then we had the Civil War. We could not go back to those plots for almost 2 decades. And then another measurement in 2007. And actually, this is an old graph. There is a new measurement that I did in 2014. So what this shows is a plot where we had 3 measurements, so 3 fieldwork expeditions. And from these 3 measurements, we can calculate 2 fluxes. We have 2 intervals. So we have a flux of carbon growth. This is growth, the gains, we call it. And these are the losses, so from the dead trees. And we see that this is about 5.5 or 6 tons of carbon per hectare per year during the first interval. In the second interval, it increased a little bit. Whereas the losses were around 7.5 tons of carbon per hectare per year. In the first interval, and second interval, it decreased a little bit. And then the carbon gains minus the carbon losses gives the net change. And you see that in this plot, the balance was about 0 in the first interval, but then it increased a little bit in the second interval. And we do this for all plots, for all 244 plots. And this is how it looks like if you put all plots on top of one another on the same graph. So a lot of intervals, a lot of plots, a lot of data. And then from this, we summarize the long-term trends going from the 1980s to the 2000s. By calculating averages for every time period, and then we apply statistical regression analysis, we call it, to calculate a trend. Do the losses on average increase or decrease? Do the gains, the carbon additions on average increase or decrease? We do that by statistical analysis, but I'm not going to plunge into those methods, so I'm straight away going to plunge into the results then. So first of all, the first question, what was the evolution of the tropical carbon sink over the last decades? So this is the same plot, but the averaging we did on it. So the same data, but the averages. And in blue is the new trend that we found for Africa, and in brown is the data for the Amazon, which has already been published in 2015. But our aim was now for the first time to be able to compare these long-term trends in the net sink between Africa and the Amazon. So this is the net sink. This is the balance between carbon gains and carbon losses. So this shows that since 1985 to 2015, African tropical forests have been actively taking carbon from the atmosphere. So they were a net carbon sink for all of these decades. The same thing counts for the Amazon. So the Amazon was also an active carbon sink. The balance was positive, but we can see that the strength of the sink in the Amazon has been going down severely since the middle of the 1990s, whereas in Africa it has been stable. So by this result, we can already say that the sink strength of Earth's two largest tropical forests have diverged, and this is the main figure of the Nature paper. However, we did a side analysis on the most intensively monitored plots, the most reliable data for the African sink, and these showed us that the African sink has been declining a little bit, so it's not that stable anymore since the 2000s. Actually, really since 2010, the sink has been declining a little bit. So this is a side observation that we had. African tropical forests have been a stable carbon sink for decades, but since 2010, we seem to observe a decline in the sink strength. So we also calculated, this is our table 1, we calculated the total sink, or the total capacity of the forests for the whole of the continents of Africa, the Amazon, and then we also have similar figures for Asia, but Asia is such a small forest that they are not really significant in this. But we aim to calculate for the first time now how much the tropics as a whole, how much carbon the forests sequester from the atmosphere. So this is expressed in billion tons of carbon per year. So not anymore on a per hectare level, but on the whole of the rainforest. And here we see when summing up Africa and the African and the Amazon sink to get the pantropical sink, we see that the highest, the point at which the sink was the highest was in the 1990s. And together, all these forests together started to decline. The sink size started to decline up to now. So this is a very worrying result, and this is actually why our result gets so much media attention. This takes into account our per hectare sink trends, but also losses of intact forest area due to deforestation. So this table shows both trends. Now, what are the drivers behind all these mechanisms? What are the drivers behind the carbon additions to the system, and what are the drivers behind the carbon losses from the system? The easiest way, we actually see that. So this is the first image I showed you was the net carbon sink, but this is boiled down into the carbon gains. The additions to the system is this one, and then the losses to the system. And we see that this divergence between the Amazon and Africa is largely driven due to a difference in losses, mortality. We see that the losses, the mortality in the Amazon, the brown line, has been racing up since the 1990s, whereas losses, mortality in Africa has been kind of stable over the last 3 decades, whereas the additions from tree growth in both continents seem to be very similar. So the difference is largely driven by losses from tree mortality. We can actually, people who know their plots can actually, like for example me, this is an image from a dead tree in Yangambi. When I went there in 2017, I really saw an increased number of trees that were dead. So to people who know the forest a little bit, I often get these questions from journalists, but it's difficult to see, but you can actually see it if you have been monitoring these plots for a long time. So what are the drivers on the carbon gains? We did this quick analysis on not a quick analysis, of course, but this is maybe the simplest way to show it by just bivariate relationships between the gains, then CO2, temperature, and MCWD is a measure of drought. We actually see a positive CO2 fertilization effect on tree growth. So trees grow more because of CO2 in the air. But then we also observe an increasingly negative effect of higher temperatures and drought on the gains. And that is why in this graph, you see how in the beginning, in the 1980s and the 1990s, the growth of the trees was also kind of racing up. But now this trend is leveling off a little bit because the negative effect of temperatures and drought is counteracting the positive effects of CO2 fertilization. So we did find significant relationships between CO2 concentration, temperature, and drought. This is also for the first time that we do this on such a large data set, combining Africa and Amazonian data. But now the big question is, what is driving these carbon losses? Do we also find these relations? And the answer is no. We did not find direct relation between CO2, temperature, or drought and carbon losses. So what is then driving this difference between what is driving mortality? How can we explain mortality trends over the long term? And the answer is quite complex. Actually, by comparing the correlation between productivity and mortality, we found that there is a direct relation actually between productivity in the past, so past growth of the trees, is related to the mortality that we observe today. So we actually found out that there is a significant internal feedback mechanism. Because of this increased growth in the past, in the 1980s and the 1990s, we now observe, especially in the Amazon, accelerated mortality. And so we estimated a metric called carbon residence time. It's a complex metric to explain, but it's actually a function of the productivity. And we found it expresses how long carbon stays in the system, for how many years carbon stays in the forest. And it is actually calculated by using productivity. But we found a positive effect between this carbon residence time, so actually tree productivity in the past, and mortality. So this is an important, but you cannot read it so well, but it means that we see a typical high gain, high loss forest dynamics pattern. You can actually compare it with overfeeding animals. So if you give too much food to an animal, or in our case to a forest, you accelerate his dynamics. So you will get too much productivity in a very short time frame. Then your animal or your forest becomes ill, and then you get an accelerated mortality. So I try to explain it a little bit in this way. We can also see if we subset our data, and that's an important supplementary analysis that we did. If we tear apart our African plots into the plots with high productivity in the past and plots with lower productivity in the past, then we clearly see that the African plots with the higher productivity in the past are now the ones that show increased mortality. So by subsetting our analysis, we could confirm that past productivity plays an important role on the mortality that we observe today. What we could also see is that the plots that grow most, if you look at the whole database, so the plots that had the highest gains in the past, and they have the highest turnover rates, and so the lowest carbon residence time, are the Amazonian plots. And those are the plots that show this fastest, let's say, dynamics and the fastest response now of mortality on past tree growths. And that is what drives the divergence between Africa and the Amazon. We can actually say that because Amazonian forests are so much faster in their dynamics, or African forests are so much slower in their dynamics, they are about 13 years behind Amazonian forests. So we see this effect of this increased mortality 13 years later in Africa than in the Amazon. So our conclusions from this complex analysis shows that CO2 fertilization effect is increasingly counteracted by the impacts of higher temperatures and droughts on tree growth and mortality. And this process is modulated by internal forest dynamics, with fastest forests, in this case the Amazonia, and Amazonia saturating first. And then quickly, how does this look like in the future? How will these trends continue in the future? For this, we did a more complex analysis, combining all parameters, CO2, temperature, drought, but then also this carbon residence time, the feedback factor between mortality and gains, into a big model. And we used this model to calculate future trends of the net carbon sink. So what you see in gray is what I presented in the beginning, is this positive net carbon sink in Africa being kind of stable, decreasing a little bit since 2010, and in Amazonia going down heavily. And the colored lines are our predictions. And we see that predictions and reconstructions, and we see that the reconstructions match quite well with the observed trends in the time frame where we have observations. So this shows us that we can be confident that the trends in the future will also probably be quite correct. And we see that by this we could estimate that the African sink will decline by 14% by the 2030s, while the Amazon sink will actually reach 0 in 2035. So here the African sink will, the Amazonian sink will disappear. So this is quite worrisome. And I always conclude that, however, that we observe this significant decreases in the sink and in this ecosystem function of tropical forests, I have to stress that intact tropical forests always remain major stores of carbon, and they are key centers of biodiversity. This is a message that I always give to journalists. So we are actually ringing the bell a little bit, that rainforests are going down in this ability to sequester carbon, but they are still really, really important reservoirs. But so, however, their ability to sequester carbon is waning, is decreasing. And if we calculate it in terms of CO2, we could actually calculate that in the 1990s, intact tropical forests were able to sequester 17% of our human-made CO2 in the atmosphere, whereas now in the 2010s, this has declined to only 6%. So this ability of tropical forests to sequester carbon is decreasing really, really fast. And we actually found that this is something that the big models used by the IPCC, the big Earth system models used by the IPCC, did not foresee this, did not predict this fast decrease. These models typically predict that the two sinks will probably be stable in the future. But so now, using our ground-based data and our big analysis, we show that this will not be the case. So intact tropical forest carbon sink is set to end far sooner than even the most pessimistic climate-driven vegetation models predict. So our paper is a call to reassess those models and to try to capture what they mostly fail to capture is this complex relation between productivity and mortality. So we have to improve the models, and we have to also revise the outcome of the models and the policy that is based on those models. But we also have important implications for scientific research. We have to continue our on-the-ground monitoring to reduce the uncertainties in our analysis, and to solve a few questions that typically pop up. So typically the questions I get is, what are the regional scale trends? We show the trends on continent level, but of course there are differences between the Congo Basin and the Lower Guinea and West Africa. Our data is not big enough now to solve that question, but if we continue monitoring, we will be able to show the differences and which forests are still important carbon sinks and which are less important carbon sinks, and that will be really important in the future to differentiate. Improve Earth system models. And then we have policy implications, is that our climate change impacts in the tropics may become more severe than predicted. So what we did is show the invisible impacts of climate change on the forest. So what you see more and more in the media are these forest fires, which are the direct impacts of climate change on forests. But even forests that are not burning, that are not cut, even intact forests, they suffer from climate change, and their ability to cope with it is going down. So it means that an earlier date to reach net zero anthropogenic greenhouse gas emissions will be required to meet any given commitment to limit the global heating of Earth. This is the message that we give to policymakers. And apart from cutting emissions, we also need to protect our existing rainforests, because they are still major reservoirs of carbon. And we need dedicated efforts to protect African forests. Actually, what our analysis now showed for the first time is that we see this Amazonian sink racing down very, very quickly, But the African sink, although it is going down a little bit, has been stable for decades and is not going down so much. So it means that African forests will play an increasingly important role in the global carbon cycle. And actually, I more and more to journalists, I give the message that our paper shows that we need to invest in protection of African forests, because we will need them more than ever in the future. And of course, I also stress the fact that we need to, apart from protecting existing forests, we need to invest in planting trees. We need to invest in forest regeneration, because there is no machine in the world that can do what forests can do, take carbon from the atmosphere. So we really need urgent action now. That is what our paper says. And I don't know if there is still some time to Jonas. Can I go on to show what we will do in the future, our future research, or should we cut now? 5 minutes? I have a few more slides. Hmm? Yeah. So in the future, we want to of course we want to expand our data set, and in the beginning I've shown you the map and the fact that we have a big gap, or the central Congo Basin is not covered as much as it should be. So I think that this is a role the AfricaMuseum will play in the future, and our team will focus more and more on this. Is to improve our data set from the central Congo Basin. We have now, as of now, we only have 4 clusters of plots located in 4 different areas, and we aim to install 2 new clusters in the near future, and of course also go back to those clusters and remeasure the trees there. So by 2022, we'll add 2 clusters and recensus the other 4 clusters, and altogether by 2020 we will have a decade worth of data from the inner Congo Basin. So this is what we aim for in the near future. And I tried to do a first regional analysis, because I was asked to do it so many times, on the existing plot data to show the difference between the Congo Basin and Western Africa. And this is the Congo Basin, so our data is far more limited. We only have a few plots, so we only cover about 7 years of data as of now, whereas this is Cameroon, Gabon. You see that we have a lot of data there, and this is West Africa, Sierra Leone, Liberia, Ghana. So we also have a lot of data there. But the first thing that we see when we do this region analysis is that the Congo Basin has, as of now, the largest sink capacity. So our few plots in the Congo Basin show that they have actually almost at least double the sink capacity of forests in West Africa. They have a larger sink capacity than forests in the Lower Guinea, and their sink capacity seems to be increasing, whereas the one in Lower Guinea, Cameroon, Gabon, is going down. But of course, we need more data to confirm this, and this will be something really important because it's only a few plots that we have in a database. So the Congo Basin is small in our analysis, but the Congo Basin represents a huge amount of forest. So if we will be able to confirm this in the future, we will have something really important to stress how important the Congo Basin is in the global carbon cycle. This actually kind of shows now that in the future, the Congo Basin may be the only part of intact tropical forest that will actively keep on sequestering carbon, and that will increase even this capacity. I hope we will be able to confirm this. So yeah, this is a wrap-up of what I just said. Apart from that, we're also interested in the history of those forests, and to see if impact to see if trends or impacts from the past, or let's say disturbance in the past had an impact on the forest dynamics that we observe now. So there are some people who say that the trends that we observe today in forests being an active sink, in Africa, this may be an effect of past disturbance, and the forests are now regenerating. To be able to exclude that hypothesis, to say that the sink that we observe today is just let's say a response on past disturbances, We are going to use our charcoal analysis, charcoal identification, which we do in the wood biology lab here in the AfricaMuseum, to sort out for each of our plots what the past disturbances were and how it had an impact on forest composition and dynamics today. So we will combine these measurements of forests with our analysis that we have been doing here for a long time as well. And then finally, we will also combine forces with Ghent University, who invested a lot of money in putting up a Flux Tower in Yangambi. Then this Flux Tower will directly measure daily net CO2 fluxes, daily net N2O fluxes, methane fluxes, evapotranspiration, and will also provide high quality climate data. So by installing plots in the footprint of that tower, we will be able to directly compare the trends that we observe from directly measuring trees with another kind of measurement, very detailed measurements from a Flux Tower. So in the future, this will also give us a big opportunity to confirm our analysis and to check whether our analysis holds up. And then I always end up with this other opportunity that we have apart from the Flux Tower. We now have a wood biology that is installed in Yangambi, and that will be used as a hub to expand our research over the Congo Basin, because Yangambi is really the center of the Congo Basin. Our lab that we have there will play a really big, important role in our future research. And for those who are interested in the lab, there is a link that you can use, and there's a little movie that you can see on how the lab is set up. And that's it. I hope I was a little bit clear, and I hope there's still a little bit of time for questions.